Yeah, can you see the slide? Okay, okay, so I should begin formally then. Okay, okay, so till yesterday we were discussing some foundational issues in quantum mechanics and how they are related to quantum information. And I had talked about the quantum measurement problem, for example. Then I talked about the Epa paradox. And I had also talked about how one can try to understand more regarding these paradoxes with an aim to connect with quantum information theory, understanding quantum information theory. And one of the key, points there is to understand how the classical world emerges from quantum mechanics. If you have a large collection of quantum objects, if you go to the macroscopic domain, how you see the classical world to be emerging. So we just thought that we should start studying how this problem can be tackled. And in an attempt to do that, I basically introduced you the density matrix formalism. And in the density matrix formalism, there is these very elementary concepts about density matrices and their normalization, etc., regarding mixed states, basically, how mixed states are different from pure states. So now the point is, we thought that let us try to understand how this classical world emerges, or in the other world, in fact, decoherence. Yes. Okay, okay, maybe yes, maybe it is too small. That's the problem. Is it any better? Or let's see. Now see this one. I don't know. This is the problem which we should have sorted out much earlier. So I just logged in at 2:45, but nobody was there. So is it any better? It is better? Okay. Okay. So I'll just take this to the extent possible. Right? Okay. So this is okay, but in this format, it seems that, yeah, I can't see anybody's chats. Anyway, you have to tell me. Okay, fine, no problem. So is this slightly better? So I'll zoom it further to 100%. Now? Okay, so let us keep this format then. Okay, fine, thank you. Okay. So then but I find the slide shaking somewhat. I don't know what the issue is. At your end, is the visible slide still shaking, or is it still? Yes. So I don't know what the issue is. So let us do with this one, because yesterday I was trying to show you PowerPoint slides, but unfortunately they couldn't be Zoom. So should I go back and try to obtain PowerPoint slides? This is the better option. Okay, but still the blinking continues anyway. You will have to bear with it. No problem. Anyway, so the idea is that any quantum system cannot be absolutely isolated from its environment, and this is even more true if you use an apparatus or a measurement device to obtain some information about the system. Since that measurement device is a big device, it's a classical device, in no way can it be separated completely from the environment. So therefore, as we learned from our previous slides, that quantum mechanics indeed is contextual, in the sense that if you want to extract any information from the system, then the context is important. You cannot just simply ignore the context. So in this case, you'll have to consider not only the system and the apparatus, but also the environment. And since you cannot monitor the full degrees of freedom of the environment is a huge system. It can contain thousands, millions of particles, atoms. So you do not have full knowledge of this environment. So you are forced to consider the density matrix of the whole system. So that is system, apparatus, environment taken together. So now again, if one tries to apply the Schrodinger equation to this system, so what will happen is that this system will evolve in time to a combined, now if you think that you can only consider the states, what you know of the environment, it will evolve to some kind of this expression, where your phi I are the required basis states of the system, AI are the basis states of the apparatus, and EI are the basis states of the environment. Remember, we are modeling everything in a quantum mechanical way. So these are the bases. And now the total system, if you take all the environmental degrees of freedom together with the system and apparatus, is still a pure state, right? Okay. But as I was saying, the environment has too many degrees of freedom, and it is not possible to monitor all of them individually. So therefore, what we do, in order to focus back and obtain information about the system and apparatus, we trace over the environment degrees of freedom. So this is the expression for the density matrix of the system and environment after taking out the trace of the environmental degrees of freedom. Now you see, in the diagonal coefficients, of course, remain the same, alpha, beta. These are to do with the system. However, the off-diagonal elements of this density matrix contain an extra factor z, and most generally this extra factor z, or the coefficient z, decreases rapidly with time, and in due course this density matrix reduces to a completely diagonal density matrix. That means the off-diagonal elements go to 0. Now what do the off-diagonal elements signify? The off-diagonal elements signify superpositions among the various macroscopic states in this case. However, in due course of time, you observe the apparatus to be completely free of such superposition. You indeed get an actual one particular pointer value, and this density matrix indeed tells you that after some time, the decoherence time, you will indeed get no superposition between the different diagonal elements of the apparatus, but on the other hand, you will get a perfectly diagonal matrix signifying one possibility of either this value or this value. Okay. So the mix, in the mixed final state, there is no superposition of the macroscopic apparatus state, and in this sense, you can say that the classical world emerges in this program of environment-induced decoherence. Okay. So how does it happen in practice for a particular example? Now you consider again a state which is, say, Ci phi I are the eigenstates, and apparatus A0. We return back to our familiar problem of detecting the spin of a spin-half particle along a particular direction. And after interaction with the system and apparatus, the system evolves into a combination, entangled state between the system and the apparatus. Let us choose the initial spin state to be a superposition of plus and minus, up and down states along the z direction in the z basis. So now, after the system environment interaction, this state goes to a combination of the up state with the pointer, the macroscopic pointer pointing upwards, and the down state with the macroscopic pointer pointing downwards. And this state, you already know, it's rotationally invariant because this is the character of this state, and so therefore many bases are possible. So for instance, we can move from this z basis into plus basis or x basis or whatever. So for example, in the plus basis, your pointer points out towards, you can apply this as up direction pointer and this down direction pointer, which is indeed a superposition of these two things. Okay. So now what happens is that till now we have not considered any environment. So this is again a problem because no single outcome will emerge to this. However, if we now apply the macroscopic pointer states with the environment and take trace over the environment, then one of these possibilities will go and you will indeed be left with either the pointer pointing up or the pointer pointing down. Okay. And this also will lead to a preferred basis, because in the decoherence program, whatever you measure is with respect to a position basis. You can also imagine that all measurements finally in some way can be reduced to the measurement of a pointer on some direction. So this is naturally the physical space basis, right? And so therefore this preferred basis emerges and you get this emergence of classicality. But One more thing is important for you to realize, though the CID problem actually tells us how a classical world can emerge, it still does not tell us unambiguously how a single outcome can emerge in a measurement, because if you go back to the last slide, you see that either of these two outcomes can be possible. Of course, there can be no superposition between these two outcomes, no off-diagonal element, but both the diagonal elements still remain. It is not as if that one of the diagonal elements is going to 0. Both of them still remain. So what does this environment-induced decoherence program does? It does not certainly explain a single outcome in a measurement. However, it replaces the problem of superposition, that is both up and down outcome, to the problem, to a choice of outcomes either up or down, right? So it replaces the and problem to a slightly lesser problem of or problem. So this one has to keep in mind and understand. So this environment-induced decoherence program is, of course, a successful program in order to understand how the classical world emerges from quantum mechanics if you have large degrees of freedom, but it still cannot answer unambiguously the measurement problem. Okay, so there were many other efforts. So measurement problem, this is just a summary of the measurement problem. Let me skip it. So there are many other efforts in quantum theory to explain this problem, emergence of classicality. And let us again start with a recap of standard quantum mechanics, which tells us that macroscopic objects are built out of a collection of quantum particles. At the micro level, at the macro level, indeed, therefore, there is no identity of individual constituents because these can be entangled with other constituents. However, you have the von Neumann collapse postulate and the Bohr's classical and quantum divide. There is an arbitrary cut between the quantum particle and the classical apparatus. And now, of course, this leads to the question, as you all saw when we discussed the Schrodinger cat paradox, is a conscious observer required for explaining collapse? Okay, so means that in order to extract classical information out of a quantum system, classical information that all of us are familiar with, we can make meaning out of it. So if you want to extract that classical information from a quantum system, do you need a conscious observer, or you need to do something else with the structure or theory of quantum mechanics itself? So in the latter direction, several, works and several approaches have done over all these years. Of course, I don't have time to discuss this because originally I planned this to be part of yesterday's talk, but we are already, I think, almost 15 minutes into today's talk. So I will not be able to spend too much time on this, but I will just outline to you what are the various approaches. First of all, you have this Copenhagen interpretation, which I've already talked about. Then you have this environment-induced decoherence approach, which I have already talked about and discussed that in at least some detail. Then you also have these so-called fundamental collapse paradigms. Okay, so what are fundamental collapse paradigms? Fundamental collapse paradigms tells us that if you go into the complete depths of quantum mechanics, it is not a completely accurate theory or not a complete theory in the sense that there is something more. So in addition to the unitary evolution, you will have to postulate something else, and which are natural spontaneous collapses. For example, you say that at random times your wave function undergoes sudden jumps, and this jump is of course modeled by some operator which I have written here. I don't have time to go into all these details, but a nice feature of such an approach is that if you take macroscopic objects, then they naturally collapse, whereas you have to set some parameters, scales of some parameters, whereas single particles or small microscopic objects will remain in superposition over the lifetime of the universe. So this is a nice feature. Of course, there are several problems also, and I'm reminded of this again in this direction. The gravity-induced state vector reduction. This was pioneered by Penrose, and Penrose, as all of you know, received the Nobel Prize for Physics yesterday. Of course, he received for the, the solution formation of black holes. But Penrose is a person who has also worked a lot in foundations of quantum mechanics, and he was the one who proposed this gravity-induced state vector reduction, which has a somewhat similar character to fundamental collapse paradigm. So again, unfortunately, I have not much time to discuss this. So if anybody is interested, we can talk of it later. And there are also other approaches. For example, there is this many worlds interpretation, which was pioneered by Everett and then worked about by a lot of other very well-known people. But in the sense, this approach adds some, if you like, philosophy or metaphysics to the structure of quantum mechanics. So it is not appealing to a large number of people. So let me just skip out this many worlds approach altogether. Then there is another kind of approach which is in a way a realist approach, which is called the Bohmian approach, and it comes out from the de Broglie-Bohm pilot wave theory, which was formulated in 1952, and of course it has been, I think, among all approaches, this is one approach on which there has been a large number of works, large number of efforts trying to make sense of this approach. So what they propose is this quantum theory should accommodate something more than the wave function, and this is in terms of hidden variables. Okay. Now some of you who know about Bell's theorem will immediately object, saying that hidden variables can be ruled out. But the point is that there are certain contextual hidden variable models which can avoid the impossibility proofs of von Neumann and Koch and Specker consistent with Bell's theorem. So these kinds of hidden variables that one uses in the Bohm model is indeed consistent with the Bell's theorem. And in this model, what is the upshot is that individual particles indeed have real positions and trajectories in space-time. So if I go back and try to resolve this, problem of superposition of a single particle through two slits, then what will they say? That there are indeed real particle trajectories. And also, predictions of Bohmian mechanics are consistent with those of standard quantum theory whenever the latter is unambiguous. Okay, so you will see many situations where quantum theory gives exact particular predictions and Bohmian mechanics also give those same predictions. However, in certain situations, quantum mechanics cannot give you exact unambiguous predictions. In those places, Bohmian mechanics can offer some extra insight. Okay, so we will come to that. So I don't have time to run through all the mathematics because there are other topics in which I will miss in that case. However, just remember something, that in this case, rho, which is psi mod square, represents the probability density of particles which are actually occupying certain positions, as different from standard quantum mechanics, standard quantum interpretation, where psi square represents the probability of finding a particle at a particular location if you perform a measurement. And now, since you have exact particle positions irrespective of measurements, then you can write down the particle velocity, which is nothing but dx by dt, and you define something else which is called the quantum probability current, which exactly obeys the continuity equation as expected. So this is the quantum probability current, and this is obtained from the phase of the wave function. So if I write down the wave function in polar coordinates, that is psi equal to r e to the power of minus is, right? So this is the wave function, r psi equal to r e to the power of is, s is the phase, and velocity of a particle is nothing but the gradient of the phase. And in this case, particle trajectory is completely deterministic and is obtained by integrating the above velocity equation. However, you can see here that there is some implicit non-locality which is built in. I mean, not only implicit, it is quite explicit here, because the velocity of a particular particle, see, if I have a collection of particles given by coordinates x1, x2 up to xn, and I want to find out the x component of velocity of this particle x1, this depends not only on its own self x1, but also the other particles x2 up to xn. So you can see how savage, how extreme the problem of non-locality is in this model, Bohmian model, right? So Bohmian model essentially follows the Hamilton-Jacobi approach of quantum mechanics. Again, I don't have time to explain it to you. If anybody is interested, so I will talk about it later. But if you look into this Hamilton-Jacobi equation, then in the Bohmian model, you get on the right-hand side, of course, you get the gradient. Okay, del of S should be here, that is the phase of the wave function. You get the classical potential. Additionally, you also get something which is called the quantum potential, which actually comes from the gradient of the real part of the wave function. Okay, and this quantum potential is actually responsible for the non-locality of the whole problem, because as I said, this quantum potential depends on all particles which occupy all places in the whole configuration space. So basically, what is the physics here? The physics is that you have a particle but which has some kind of position and trajectory without any measurement, but you also have the guiding quantum wave function, which actually tells you how this particle will move in space and time. Right. So again, let me just skip this slide and come to an example of application of Bohmian mechanics, so just to give you an idea how this thing can work. So this Bohmian mechanics has been applied for the study of the interference or superposition in the two-slit problem. So these are two slits, one is here, one is here, and from here there are single particles which fall one at a time on these two slits. At any instant of time, there is not more than one particle in this setup. And of course, this particular diagram is for photons. So for example, we have written Bohmian trajectories for photons. However, the standard Bohmian mechanics is formulated for massive particles. You'll have to extend it for massless particles, as we did in this work many years ago, almost 20 years ago. But just a simple feature, you see that, again, if you have a screen anywhere on the right, you will get exactly the same interference patterns that standard quantum mechanics predicts for you. So in this sense, Bohmian mechanics will give you exactly the same predictions as standard quantum mechanics give you. However, it will also give you something more. Okay, for that, just closely inspect the trajectories of these particles. These are real trajectories, quantum trajectories from Bohmian mechanics, trajectories of photons. But one thing you can actually observe if you look closely from here is that if you look into the photons coming out of the slit here on the upper plane, that is the slit on the top, then you will see all the trajectories lie on the upper plane itself. In other words, there is no trajectory of a photon which can come out from the upper slit and cross the symmetry line and go to the lower plane. Similarly, it happens for the photons which come out of the lower slit. There is no photon or no photon trajectory which can actually traverse upwards, cross this plane of symmetry at y equal to 0 and go to the upper plane. Right? So this prediction is completely different from what you have in standard quantum mechanics. Because remember, standard quantum mechanics, all it tells you that even though there is a single particle, it can come from any of these slits, when on the right hand side, the probability is given by psi mod square. It never tells us that there is no coming of a probability or no coming of a particle which enters through this slit but comes to an upper plane. So in this sense, it is a remarkably different prediction. And I should also mention that similar kinds of trajectories were also found, photon trajectories, through another approach. So that is an approach of weak measurements. Now, I don't know whether during the course of this lectures, anybody will explain to you what weak measurements are, but they are also a fascinating way of understanding quantum mechanics, a different approach of measurements in quantum mechanics. And even using these weak trajectories, you end up with exactly the same trajectories, right? Weak trajectories, in a nutshell, if you want to know, very heuristically, you say that the photon is measured weakly along all these paths so that its state is not disturbed drastically. So if you want to apply weak trajectories and you plot the trajectories as these people did in a science paper in 2011, you replicate exactly the character of trajectories that is found using the Bohmian approach. So all of this is extremely interesting, and quantum mechanics will of course give you this interference pattern, so there is no contradiction with standard quantum mechanics, but it cannot predict an extra feature which I just mentioned. Okay, so I think we come to an end of this part of this talk. That is, I would have liked to complete yesterday, but it could not be, it could not be completed for some reason. I would like to end this portion by saying that our target is to study quantum information, and so far we have understood, or so far we have seen, that superposition and entanglement are the two great main features of quantum mechanics, which play a great role in quantum information. And due to this entangling character of quantum mechanics, quantum information can be non-local, and quantum correlations that we already seen in elementary examples of spin-off particles and polarization of photons, they are a resource which due to their non-local character can be much stronger than classical correlations, right? But the point now is, and this was indeed referred to Einstein by something like a spooky action at a distance. Of course, in the real world, we know that there is no real action at a distance. There is no violation of the special theory of relativity. However, there is some kind of non-locality. And in order to understand this quantitatively, how much more can quantum correlation be stronger than classical correlations? Now we have to delve into the study of something else. And that something else is in another sense, the remarkable, quantification of quantum non-locality. So there are some references for this part of the talk. If, somebody is interested, they can take it down at some point of the meeting. But today we move on to the next talk. Basically, this is formally the lecture 2 that I planned for on fundamental aspects of quantum theory and quantum information. So my original plan for this lecture was to start with description of quantum non-locality, how you can form a quantitative idea of departure from classical locality and realism, and this is definitely through Bell's theorem and Bell's inequalities. So I would like to discuss Bell's theorem and Bell's inequalities with a few details, and afterwards I will move on to quantum information processing applications. And of course there are many applications, as all of you know, key generation, cryptography, computation, etc., etc. But I don't know how much time I will have to consider whatever application. Let us go and let us see. Okay, so I see there is a question from Jatin Ghai, who said that how do we get an interference pattern if photons can't cross the symmetry line of two slits in Bohmian mechanics? Right, fine. So as I said again, perhaps I said too quickly, that although the trajectories do not cross, but there is indeed the guiding wave function or the quantum potential which exists at all points in the space, configuration space. So the quantum potential due to the slit 1 is also present on the lower plane. Similarly, quantum potential due to the non-vanishing wave function at slit 2, which is below, is also present in the upper plane. So this causes the interference patterns. And the interference pattern you are seeing clearly because you are seeing some bunching and anti-bunching of trajectories. So of course there is interference, but this interference is caused by the quantum potential, right? Okay, so I don't see any other questions, so let me continue with the present talk, right? Okay, so next, this slide I've already talked to you. See, our idea is to study non-locality in quantum mechanics. And how do we study non-locality? This is done through Bell's inequalities. So this offers a quantitative measure of violation of local realism, right? So the classical hypothesis of realism and locality you are familiar with, because yesterday I talked about the Epa paradox. From there you learned what is realism and what is locality. Now how can one apply on a real physical problem? Okay, so realism, as I say, I can describe it like this. Suppose there are two particles which are prepared at A and B, and now suppose these particles have dichotomic properties. These have two properties and with two values each. For example, for classical objects or classical balls, you can consider two types of properties. For example, you can consider their color and their gloss or shine. And for classical properties, of course, color can take you infinitely many values, continuity of values, similarly gloss. However, if you take an analogy for quantum particles, particularly spin-off particles, you can think of two types of properties. One is spin on the x direction and the other is spin along the z direction. And these two also individually can take two values each, plus minus 1 or up and down spin. Okay, so these are two particles with dichotomic values. And what does realism means? That as with a classical ball, your color and gloss of a ball is there at preparation, irrespective of the fact whether you measure it or not. For quantum particles, one can just take a similarity and analogy and assume that by realism we mean that the spin along the x direction has a particular value, +1 or -1, whether we measure it or not. And similarly, the spin along the z direction has a particular value, either up or down spin, whether we measure it or not. So this is realism. Now, what does locality signify? Locality signifies that when I measure a particle A, I cannot modify instantaneously the result of measuring particle P. Again, you can see that suppose there are two particles A and B which are located at some spatial distance, they are spatially separated. And now if I measure the particle A and somebody wants to measure the particle P, by the act of my measurement, I cannot instantaneously affect the result of the other person measuring particle P. So anything which I do, that the consequence of my action has to travel to the other side at most with the speed of light. Nothing can travel faster than the speed of light. This is what is meant by locality. And okay, so now the Epa paradox again I discussed last time. I mean, what it tells us that Epa assumed that any complete description of the world must respect local realism. However, local realism is violated by quantum mechanics. So quantum mechanics is not consistent with the local realistic description. Epa thought that quantum mechanics is not a complete description of the world. However, if we want to study this departure from local realism, then we have to apply a mathematical model to this local realism, and that is exactly what was done by John Bell in the 1960s. Okay, so in order to understand the structure behind Bell's inequalities, let us first try to understand how you can obtain correlations of expectation values on spins of two particles. Okay, so now let us say that two spins are in this particular entangled state, which you know is a Bell state, right? These are two spins of two particles, and Alice measures the spin of particle A along the z direction. So this, her operator is given by sigma Az, and she obtains the outcome A, whereas Bob will measure sigma B, that is particle B, along some direction which I label like this. It is by this theta, this direction, Bob's measurement direction is labeled, and this theta lies in the xz plane. Okay, so this is x, this is z, theta lies in the xz plane. And Bob will again, because he's also measuring a spin of particle, he will also get some value which lies either +1 or -1. Now the question is, suppose I want to find out the correlation of these two measurement operators, that is A measured by Alice and B measured by Bob. On the other hand, sigma ZA and sigma ZB. I want to find out the correlation of this joint measurement done by two different parties. So what will I do here? Okay. So now in quantum mechanics, I am considering two properties which are spin along two axes, sigma x and sigma z, and we can rewrite. So originally what I had was this state, which was written in the z basis, but of course this is rotationally invariant, I can also write it in the x basis. Okay. So in fact, if one measures sigma x, then Alice and Bob will obtain the same correlation, right? Because this state is invariant under rotation. So now let me try to again explain this joint measurement correlation. So I take the state, which is nothing but this one, okay, and I take this operator, this is sigma ZA, sigma BB, and I try to calculate the expectation value of this operator in this two particle entangled state, right? So this is very simple. So of course, if I expand out, there are four terms here, and the first qubit here represents the first particle, the second one represents the second, similarly 1, 2, and all these are expressions here. Okay. And of course, sigma ZA is Alice's measurement. So you have to take between the first two things. So this is between 0 and 0. So 0 and 0 here, whereas sigma BB is Bob's measurement. So you have to take between the second particles. This is 1 and 1. So 1 and 1 here, right? So this way the measurement can be worked out. However, you can see that two of these terms will drop out immediately. Why? Because I have taken already this Alice's state as Z along the spin up along the Z direction. So this is an eigenstate of this operator 1. So this will just return back this operator. However, this 1 is orthogonal to 0. So therefore, this term drops out. Similarly, this term drops out. So these two terms remain. And since sigma B is along a direction theta, so both of these will give minus cos theta, which will give you minus 2 cos theta, and half will cancel with 2. So you get minus cos theta. Okay, so this is a very simple calculation. So now just keep this calculation in mind, that if you want to take a joint correlator of two measurements which are inclined at an angle theta, the joint expectation value in quantum mechanics is given by minus cos theta of spin-off particles. So just remember this. Okay, remembering this, now we return to the actual problem, the actual Bell's experiment. So there are two particles which are entangled, and Alice has access to one particle, and Alice can perform measurements in two possible directions which are labeled either by this A here or A prime. So this is Alice's choice. On the other hand, Bob has access to the other particle of the EPR pair or the entangled pair, and Bob has the choice of measuring either along B or along B prime. Okay, so now if I want to take the joint correlations of these expectation values, then just from the last slide, whatever we learned, you see that they are just given by the angles between these respective measurements. For example, AB, the angle is theta, whereas AA prime is phi, right? So this is very simple. This is just application of the earlier result. Okay, so now I'm just repeating myself. The correlations among measurements are then AB is equal to A prime B prime is minus cos theta, whereas A prime B is minus cos theta minus phi, AB prime is minus cos theta plus phi. So now, with the help of these correlators, I want to calculate an object which is in a sense, which is an algebraic sum of these individual correlators. 3 of them will come with plus sign and 1 with minus sign, right? So let me define a expectation value, which is also called a Bell sum, which is nothing but an algebraic sum of these 4 different correlators. And now the point is, in quantum mechanics, I know how to calculate the value, but now suppose I want to do it applying the notions of locality and realism. Okay, so how can I apply the notions of locality and realism? For this purpose, just consider that at each measurement, I should be able to calculate again the value of this operator. This I just defined for you, and then if I take many runs of the experiment, then the expectation value, of course, is given by the average of outcomes obtained in these 2 runs. Okay, all these runs. Now, the notion of realism comes as follows. So suppose I measure the spin along some direction A. So then I say that the property of spin, but I do not measure the spin along direction A prime. However, I still say that because it was prepared by somebody, so the spin along A prime is real. That is, the spin along A prime it has a definite value indeed, irrespective of whether anybody performs a measurement on A prime direction or not. So this is the statement of realism. Okay. So therefore, if I want to calculate this SK, this sum of these 2 things, then what I can do, I can just express. So these 4 terms, as you saw from here, are nothing but A prime, B prime, AB prime minus A prime B. But now I can just take a combination of these BB prime and write that about the earlier expression like this: A, B plus B prime minus A prime, B minus B prime. So this is just simple algebra, nothing else. Okay. However, remember that I am measuring only A, but then using the notion of realism or reality, I can say that since the particle with Bob was also prepared in a spin half state, so therefore the sum of the expectation value of these two measurements, if Bob were to measure it, would be nothing but either they would cancel out, okay, right? So either they will add up and produce 1 and 1, or they will cancel out. 1 minus 1 gives 0, or they will add up minus 1 give minus 2. So you see how realism is applied. So Bob is not measuring, but Alice is saying that if Bob were to measure, then Alice were to get this. Okay, so Bob were to get this. So now I will just, in this expression, I will substitute either 0 or plus 2 or minus 2. For example, if I substitute 0 here, then naturally this will be plus 2. Okay, so in the end, what I will get Sk equal to either plus minus 2 sigma A or plus minus 2 sigma A prime. Nothing more, nothing else. Okay, now I apply the tenets of locality to this problem. So the point here is that the fact of measuring B and B prime does not change the value of A or A prime. So A or A prime will have outcomes either plus or minus 1, right? So remember that here, I think what we were saying is that if Bob did not measure, then also his value would be this. But locality is saying that if Alice were to measure, then nothing would change on Bob's side. And if Bob were to measure, nothing would change on Alice's side. So completely then this Sk reduces from the last slide. Sk is plus 2 sigma A reduces just to Sk equal to plus minus 2. So then what do we have? This combination of expectation value, combination of these two terms, that is S, will lie between minus 2 and plus 2. So what magic happened? No magic happened. I just applied notions of reality and locality on this problem and tried to calculate the correlations or joint measurement values of two spin-half particles which are in an entangled state. So I get, applying the notions of locality and realism, that this sum of these correlators, algebraic sum of these correlators, will lie between minus 2 and plus 2. However, what we do in quantum mechanics, we can immediately see, we can calculate the calculation that I did for you earlier. I will just go to the next slide and show that this mod of S turns out to be greater than 2. Okay, so therefore quantum mechanics violates Bell's inequality, and therefore one of the two hypotheses, either locality or realism or both, is not true. Okay. Okay, so there is another question saying, what do we mean by correlations, right? So correlations in this sense are when we are jointly measuring these A and B, right? So A is being measured by Alice, B is measured by Bob, and we are taking the outcomes of both measurement together and we are getting the correlation. So that is meant by correlation between different measurement outcomes. For example, in this term, the third term, the correlation is between the measurement outcome A by Alice and measurement B prime by Bob, right? So this is what we mean by correlations. Okay, so now, as I said, quantum mechanically you can calculate this object and you can choose some simple values, simple directions. So A can be chosen along the Z direction, A prime can be chosen along the X direction, B prime can be chosen in the B can be chosen in this direction, that is negative X and Z plane, whereas B prime can be chosen in the positive X Z plane, right? And now you again apply the simple calculation, what you learned earlier. So all these are given by the cosine of the angles between these two directions, and for all them you get either 1 by root 2 or plus 1 by root 2. Now, if you sum all of these up, then for these particular directions of measurements, what you get is minus 4 by root 2. That means minus 2 root 2, which is certainly less than minus 2. But your classical realism or local realism told you that this can never be less than minus 2. So therefore, you see that local realism or Bell's assumption of local realism is indeed violated by quantum mechanics. So this part, there are some references, John Bell's original work, and also the pioneering experimental works of Aspect Group starting from 1981. Okay, so quantum mechanics and quantum entanglement and Bell inequality violation has a checkered history. So people have calculated Bell violation by many different kinds of entangled states. The Bell state violation I already considered earlier, and in this case the quantum mechanical value is 2√2. However, you can also consider the Bell violation by non-maximally entangled states. In fact, in the lab it is very hard to prepare and preserve in information processing maximally entangled states, so you have to do with non-maximally entangled state. And for this, these coefficients 1 by √2 is replaced by some constant complex value C0 and C1. Of course, the C0 square plus C1 mod square should be equal to 1. And in this case, you can easily work out that this Bell sum will be given by 4√2 C0 C1. So for young students who are learning this for the first time, I offer this as an exercise. This is a very simple exercise. Please do this exercise to get familiarity with this notation. And similarly, you can also do another exercise. For example, this is the most general state in these 2×2 basis. I can express as this as A00, B01 plus C10 plus D11. And in that case, you just compute this expectation value, again defined exactly similarly, and show that this is equal to 2√2 times C phi, where C phi is something important. By the way, this C has nothing to do with these C0 and C1 and nothing to do with this small c. So this is capital C, and C phi means for a particular state which I am talking of. So for this particular state, which is given by phi, so C phi is equal to given by 2 mod of AD minus BC, and this is indeed a measure of entanglement which is called concurrence. So during the course of this workshop, I hope somebody will discuss such measures of entanglement and how these measures are obtained. So this is a measure of entanglement, and then you will see that in this case the Bell violation is directly proportional to the measure of entanglement in this state. So please do it as an exercise. So this will make you somewhat familiar with such notions. Okay. So so before coming to the end of this part of non-locality of, given by Bell violation, let us again try to relate with what we learned earlier regarding large states, because remember that practical information processing has to do with large states which has large particles. So let us now consider not just 2 spin-half particles, but let us consider a collection of n particles, capital N particles, and also let us say that these particles have macroscopic characters, so that they just do not have spin half, but they can just have any arbitrary spin j. If a j can take half in the sense of half, 3 by 2, 5 by 2, so on and so forth. So half integer values. Let us restrict j to half integer values. Okay. So I can do similarly in this case also. I have to define a measurement operator. In the earlier case where I was talking of spin-half particles, I use the Pauli spin operators, but now I will make a generalization of Pauli spin operators and define some kind of operators given by S. Okay, and S can measure the spin of the spin with value J. Okay, and in place of your Bell sum, which is given by S, which is an algebraic sum, I can construct another sum. Remember, the Bell sum was also, in a sense, the correlation of joint measurements of sigmas, that is spin-half variables. But here we have not sigmas, but SS, which correspond to spin J observables. So I can similarly make a combination of correlation of spin J observables, and instead of summation, I can use this integral here. Okay, so this becomes easier to study in a continuous integral version. Now, as you can know that in quantum mechanics, if you have a spin J particle, its value is forced to lie between J and minus J. There is no other possibility. And now applying the same notion of reality and locality, one can similarly obtain a Bell maximum value, Bell sum. So mod of S is constrained to lie less than 2 to the power of capital N by 2, J to the power of N. So this is if you do this measurement on a state which is entangled, then on this particular state, then from notions of locality and realism, you get this upper bound. Okay. So this is the state, this is the entangled state of N, capital N number of spin J particles. And now the next task is easy. you just calculate the quantum mechanical expectation value of this operator capital A, and this is given in terms of this obtained. This is an eigenstate. It gives you the eigenvalue lambda, and you obtain the eigenvalue lambda, and again try to find out what this will be. So this 2 to the power of n by 2 jn. So expectation what it will be. So okay. So you see that as you move towards larger and larger spin, so your ratio of lambda to this classical value or your local realistic value increases. Okay. So what you find, so not only there is Bell violation, but the magnitude of Bell violation keeps on increasing to if you take particles with larger and larger spins. And this table is shown for n equal to 2. That is, for these values, we have only considered 2 particles. However, if you consider more large number of particles, the violation even increases further. Okay. So again, this is in fact work. It is one of my first works in this subject. So I was barely a student. I have just come out of being a PhD student at that time. So this is many years old. But what this work teaches us is that in quantum mechanics, if you take a quantum state which is a large collection of large number of particles, and also it can have large spins, if you still model it quantum mechanically, though there is no escape from non-locality, which is signified by the violation of Bell's theorem. There is no escape from obtaining non-local correlation. So remember, we are modeling everything quantum mechanically, and there is no decoherence here. Okay. So this is a message. Before I move to the next part, of course, non-locality is always there. Of course, it has been verified at the level of, say, 2 or a handful of particles. It is extremely difficult to verify non-local correlation at the level of more particles because decoherence sets in the real world. And it can also be used. Okay, so it can be, of course, non-locality cannot be used for real action at a distance, but it can be used for performing some very beautiful tasks. And one of a primary for such tasks is quantum teleportation, which is also very important for quantum communications. But we will also talk of teleportation towards the end of this lecture. But before that, let me talk of one simple application of the concept that we have learned. Basically, what we have learned at the fundamental level is superposition in quantum mechanics and entanglement in quantum mechanics. And so before going on to actually trying to learn the application of non-locality in quantum information, let us try to learn the application of the superposition principle in quantum information. And that is indeed learned very well and can be seen by the paradigm of quantum computing. Okay, so now let me try to move towards quantum computing. So many of you know that the next generation of quantum devices are thought to be only performing only quantum mechanical operations. Okay, so essentially, what is a quantum computer? A computer that uses quantum mechanical phenomena to perform operations on data through devices and which uses superposition and entanglement is a quantum computer. So what is the difference between a quantum computer and a classical computer which you use today or which you are using now, which I am using now to communicate with you? Of course, a classical computer also has some quantum mechanical features. However, the most important difference is that a classical computer performance is based using certain voltages which flow through circuits and gates. Of course, these are voltages flowing through circuits and gates, but the measurements, the results, the mathematical outcomes or manipulations of these voltages can be calculated entirely using classical mechanics. There is nothing quantum mechanical about the calculations based on these voltages. Whereas, on the other hand, a quantum computer, when it will be operational, it will use entirely superpositions of devices and entanglement of devices. Okay. So in a nutshell, this is the difference. And what is the need for quantum computers? The need also arises from the way the development of classical computers has been happening over the last, say, 30, 40, 50 years. For example, some of you, okay, I see that there is another question here. So Prem Kumar has asked, isn't information traveling instantaneously between two entangled particles, which is just not accessible to us? The point is that whether information is traveling or not, unless you make a measurement, you cannot know, right? But in quantum mechanics, as soon as you measure something, you reduce the state. And as you've learned earlier, at least sticking to the standard interpretation of quantum mechanics, unless you can measure the content, unless you can perform a measurement on the state of the particle, you do not know whether that particle or trajectory exists there or not. And since information is carried by the state of a particle, something which we learned first during the course of these two lectures, you cannot just comment that whether information is traveling instantaneously within two entangled particles. So this question is meaningless, at least in the standard framework of quantum mechanics. Okay, so having answered this question by Prem Kumar, let me now talk of the need for quantum computers. So as I was saying, for the last 40, 50 or even more number of years, classical computers have been developing, and more or less on the forecast of this great Moore's law, which told us that the transistors, number of transistors on chips double every approximately 1.5 years or so. So using this prediction, it was predicted again several years ago that microprocessor circuits will be actually reduced to the atomic scale by sometime in the 2020s and 2030s. So this prediction was made actually several decades ago. But we are already in the year 2020, and now today we realize how difficult it is to miniaturize further and further. Because what happens in this problem of miniaturizing further and further? This leads to many kinds of discrepancies. For example, traces of matter which lie on these chips can quickly short them out. And more fundamentally, more importantly, if you go to such small scales, I mean, forget atoms, even if you go to near nanoscales, there is many quantum phenomena which emerge. For example, tunneling of electrons takes place between two gates and between even wires. So this completely, I mean, destroys, or this completely more or less, I mean, rather, I should say, destroys the computing algorithm. So it is not simple to miniaturize to this scale. Okay, and on the other hand, all classical computer involves serial processing. So one operation is performed at a time. For example, 64-bit classical computer operates speeds which is measured in gigaflops or floating points operation per second. However, in a quantum computer, we are essentially talking of a paradigm shift. So instead of these phenomena like tunneling of electrons and other quantum phenomena we are becoming a disadvantage, we are actually trying to turn these quantum phenomena into an advantage. Or in other words, we are trying to harness the power of atoms and molecules to perform memory and processing tasks. And using this primary feature, property, a characteristic of quantum superposition, we will also be doing parallel processing, that is millions of operations at a given instant of time. For example, if you compare just a 30-bit quantum computer, you can see that it equals to the processing power of a conventional computer which runs at 10 teraflops. Just compare, go back to a 64-bit classical computer, it runs at gigaflops, whereas a 30-qubit quantum computer has equivalent processing power of 10 teraflops, which means trillions of floating point operations per second, not the billions of floating point operations per second that we are now accustomed to using just a classical computer. And this is only a 30-bit quantum computer. Okay. So the point is now we move from classical to quantum bits, as I tried to emphasize and explain right at the beginning of my yesterday's lecture. So for classical bits, the two basic states are 0 and 1, which can be considered as off and on states in computer algorithms, and these are mutually exclusive. If you have the 0 bit, you will not have the 1 bit. If you read the 1 bit, you will not have the 0 bit. However, in quantum, for quantum bits or qubits, you have two basic states, that is ket 0 and ket 1. Now, using two basic states, you can consider the superposition of these two basic states, and you can make a string which is arbitrary, in the sense you can construct arbitrary different number of superpositions. So that is a beauty of quantum information processing, that instead of just relying on mutually exclusive 0 and 1 and performing one operation at a time serially, you can perform parallel operations using superpositions of these two qubits. And why is quantum computing power useful? It has been seen that classical computing power is very limited, for example, in certain problems, for example, in integer factorization. So if you have a product of two prime numbers, then to factorize it nearly equal to prime numbers, then to factorize it using your classical computer, classical algorithm requires huge amount of computer times. Okay, and quantum computer, whereas with 2n qubits can factor numbers with lengths of n bits. So this problem becomes entirely different, entirely much more easier, much less time and resource consuming in quantum computation. Similarly, if you think of the database search problem, for example, in a very big database, if you want to unsorted database, if you want to pick out a particular information, then a classical, for the same task for which a classical computer could take 100 years, can be done within half a second by quantum computer. All of this theoretically, what I'm saying, at least if you can apply the algorithm properly. So this is a tremendous, at least in principle, tremendous power of a quantum computer over a classical computer. And practical computer applications, quantum computer applications are many. They have been realized. So, for example, in many kinds of quantum mechanical simulations where you are indeed dealing with superposed objects, superposed real objects, which you are trying to simulate, superposed or entangled objects, you cannot do with classical algorithms. Okay, so you have to apply quantum algorithms, and this have been found to be of interest and to be of, real importance, not only in physics that we are talking of, physics and mathematics, but also in chemistry, in material science, nanotechnology, even biology and medicine. So the power, the potential of quantum computers is huge. And before going off the slide, I should not forget the problem of secret key, or the problem of secrecy preservation. So this is one of the biggest problems in today's world, how to protect your data from malafide hackers. Okay, so in this also, quantum computers provide a huge advantage. Okay, so quantum bits, as I said, the first idea of performing such computation using quantum mechanical rules, frameworks, was proposed by Richard Feynman and also by David Deutsche in the 1980s. And they suggested that if we can use quantum effects for computation, it will be really very beneficial. So this slide is just a repetition. So what one can just show is that the power of different types of basis states. For example, with 2 qubits in superposition of 4 basis states, you can have many states. And if you go to 1000 qubits, then your superposition is of 2 to the power of 1000 states. So the number of accessible states rises exponentially with the number of bits. That is the whole point. Whereas in classical computation, classical bits, the number of states does not rise. It rises polynomially with the number of bits. So therefore, quantum computation offers a massive space for computing. Okay. However, as I said, that this is in principle, doing the actual task can be indeed very difficult. So this slide is again actually a repetition where qubit you form a superposition of such slide. So I need not spend time going through this slide, but I will just come to some examples of basic gates. So those of you who are physics or computer science students must be already very familiar with these gates. However, these gates are quantum operations. Okay, so quantum operation maps quantum states to quantum states, and they are linear, by which I mean that all these quantum operations correspond to unitary matrices. So they are linear unitary operations. So I can give you an example of 1 qubit gates, the X gate, the Z gate, the T gate, and also the Hadamard gate. So Hadamard gate is an important gate for information processing given by this. So what does an Hadamard gate do? From a 0 qubit, it goes to it actually produces an output as a superposition of a 0 and 1 qubit. And similarly for the acting on the 1 qubit, the Hadamard gate takes you to a superposition of this. So particularly in a laboratory, if you have a single electron or a single photon and you want to build up a superposition, what you will do, you of course in an old-fashioned way you can make it pass through a slit, but that is exactly equal to applying a Hadamard gate like this. Okay, but on the other hand, this is a unitary transformation, so this is also reversible in the sense that if you apply your Hadamard to this 0 plus 1, you will get back to 0 qubit state. Okay. Now, of course, these are 1 qubit gates, and you can have 2 qubits gate also. The prime example is control NOT gate, C0 gate, which I will also come to in one of the later slides. And in fact, quantum circuits apply similar notions of logic as classical circuits. For example, you are aware that a classical Boolean circuits can be composed of these gates and or NOT gates on an n-bit register. However, a quantum circuit consists of unitary quantum gates, which can in general act on n-qubit register. So this is again a beauty of quantum qubits. Okay, and in quantum qubits, essentially H, T, and C0 gates are seen to make to true all possible, all feasible operations. So the combination of these gates suffices for implementing quantum circuits. Okay, so in fact you can have many examples. So for example, you can consider these 2 bits, initial qubits, both 0 and 0, and 1 you can apply the Hadamard, so it goes to a superposition of 0 0, and then you take this. Okay, so this goes to a superposition of 0 0 and 1 0, and now you apply a control NOT gate and you get finally, which is an entangled state of 2 qubits. So in this case, you see the superposition is only on the first qubit. So this 0 and this 1. The second qubit remains unaffected as far as the Hadamard is concerned. But now you consider a 2 qubit joint C0 gate, and then you get a final entangled state. So this circuit is a way of creating an EPR pair or an entangled pair of particles. Okay. So now, so what we want to do, so going from classical to quantum computation, we have to go from bits to qubits. From AND or NOT gates, we have to go to unitary quantum gates. So examples you have seen, Hadamard gate or C0 gate, and you have to replace the classical circuit by a quantum circuit. So these steps you know, but the final state is also extremely important, final stage of this operation. That is, in a classical computer, you have an output bit, 0 and 1, and you simply read out this bit without disturbing it. However, if you are dealing with quantum mechanical objects, quantum mechanical qubits, whatever final qubit you have to perform a measurement on that final qubit. So implementing a quantum computer also involves performing a quantum measurement. Okay. So now, in order to actually learn or have an opinion about this beauty of quantum parallelism, let us consider one quantum algorithm as an example. And this is the famous Deutsche algorithm. It's in a very simplified version. And let us try to understand the beauty of this quantum algorithm. Okay, so suppose you have a string of n numbers, 0 and 1, and there is some function f which takes from this string to another value of m numbers. Okay, so this is the problem. Function f converts, takes from this string and takes to another this string, 0 and 1. Okay, it can take m values, for example. Now this problem can be done classically. However, I want to model this problem using a quantum circuit. Okay, and quantum circuit, for instance, I can take a 0 qubit and apply this x vector on the 0 qubit and again apply a unitary transformation which models my function. So this is an f of x. So I have to write down this f not classically but on some quantum mechanical vector space. Okay, and now using this quantum mechanical vector space, I can compute this function on all inputs simultaneously. That is the beauty of quantum superposition. For example, this x can take place, this x can take n values, the collection of 0 and 1, but I can take a superposition, and thereby taking a superposition, I can apply my function on all values simultaneously. So therefore, this contains all 2 to the n functional values. And now in the end, I will just, what I will do, I will observe only one random x of x. Remember, there can be many such x of x, and I will lose all other information, but using this observation, I will try to know how I can compute this effect of this function. Okay, so this in a nutshell is the principle of quantum computing. And now let us directly come to this Deutsche algorithm, which was one of the first algorithms of quantum computation. So as I said, let us consider a binary function that takes 0 or 1 as input and outputs either 0 and 1. So we will do a very simplified version of Deutsche. There are only 2 inputs, and taking these 2 inputs, what this function does is to either output 0 or output 1. Okay. Now, there can be 2 types of such functions, and the definitions are as follows. So I will call a function to be balanced if it outputs 0 half the time and 1 half the time. And so, for example, if I have an input 0, if it can output 0, and I have an input 0, it can output 1, or I have an input 1, it can output 1, I have an input 1, it can output 0. So this is an example of a balanced function. On the other hand, the constant function is such that the output is a constant, 1 or 0, regardless of the input, right? So input may be 0, but the output is 1, input may be 1, but the output is 1. Okay, so this is an example of a constant function. Now, what is the, so I have defined for you the problem, the function, that is what is the job of this function. Now, what is the algorithm, that is what is the task of the Deutsche algorithm. By applying this Deutsche algorithm, what do we want to achieve? So the task is as follows: given a function like this, determine if it is balanced or constant. Okay, so this is clear. So you have a function like this, you have to determine whether this function is a balanced function or this function is a constant function. So if you want to use classical computing, so what you will do, you will just try to query the function twice and collect the result twice for 2 different inputs, collect the results, and you will get the answer. So for 2 different inputs, the problem is extremely simple. But if you have n bits, right, you have n bit strings instead of the simple 2-bit string that I considered, then your number of queries rises as 2 to the power of n. That is, it rises as 2 to the power of exponentially. So just try to think, if you have a 100-bit string, then you will have to do 2 to the power of 100 operations. Just imagine how large the amount of time and resource so many operations will take. Okay, but now we will see the beauty of quantum parallel computing. So therefore, in order to do so, first of all, what we will do, we will take this initial 2 bits and create a superposition. So this is a most general superposition of 2 initial bits, 0 and 1. Okay. And next thing what we have to do, we have to design some function which is called oracle function, which will just perform for us the job that I defined in the last slide. Remember, our aim is to determine whether a given string is constant or balanced. Okay. So the circuit will be exactly like a circuit which I talked to you 2 slides ago. So it will consist of these 2 input bits. On one of these bits, I will apply a header mark, and on the other bit I will first apply an X gate and then apply an Hadamard, take these bits together and apply this oracle function. I will define you what this oracle function is, and finally what again these two bits will come out. I will completely forget about one of these qubits or bits. I will take the second qubit and apply a Hadamard and finally perform a measurement on it. That is, I will read this bit, okay, read this qubit, so at the answer output I will get either 0 and 1, okay. So I will design my oracle function in such a way that if I get output 0, then I will be sure that this is a constant function. On the other hand, if I get output 1, I will be sure that I will get a balanced function. So in this way, if I am able to devise the oracle function, then I am able to perform this Deutsche algorithm, this quantum computing in a given single step using parallel processing or superposition. Okay, so how will I design my oracle function? That is the next step. So this is the procedure. So just focus on what I am doing to the second qubit now. Okay, so the second qubit, first of all, so this is the 2 qubit state, and on the second qubit I am applying this X gate, and X gate will take the second qubit 0 to 1 qubit. And now I will apply this Hadamard gate to each of these 2 qubits. Okay, so the first qubit is the 0 qubit, and you knew from the earlier slide that if I applied Hadamard to the 0 qubit, I will get 0 plus 1 by √2. On the other hand, if I apply Hadamard to this 1 qubit, which is here, what will I get is simply 0 minus 1 by √2. Now the question is, what about this 0 function? Okay, what about this oracle function? So function output can be, I want to be either 0 or 1. Okay, so if I want function fx to be 0, so then I can take this, of course this function has to act quantum mechanically on a quantum Hilbert space basis vector x. So if I apply this x to 0 minus 1, I will get x0 minus 1. However, if I apply to this 0 minus 1 and I want output 1, then I will apply this to 1 minus 0. Okay, so just see this, if you are able to see that what does this oracle function do? Oracle function takes a binary x, is applied on a binary xy, and it goes to x comma y mod sum f of x. Okay, so the first thing it does not touch, it let it remain as x, whereas the second one it takes to y mod fx. Okay, and remember this is a binary sum, so 1 plus 1 will give you 0, 0 plus 1 will give you 1. Similarly, 1 plus 1 will give you 0, and 1 plus 0 will give you 1. So this is a binary sum. So now these x's and y's are nothing but these qubits, 0 plus 1 by 2 and 0 minus 1 by 2. Okay, so now if you apply your such oracle function in these 2 qubits, which are outputs at this stage, input for the oracle function box. So that you just have to do a one-line mathematics, one-line algebra, and convince yourself that you can write the first qubit like this, whereas the second qubit goes like this. Okay, so this is the action of the oracle function. So this models the action of the oracle function. Finally, what comes out on the right is given by this. On the upper arm, upper side, you have this qubit minus 1 to the power f0 on 0 vector plus minus 1 to the power of f1 on 1 vector, tensor product of 0, 1 by √2. Now, if fx can take either value 0 and 1, so just simply work out this algebra in one line, and you will be convinced that what I am saying is true. And finally, so on the qubit on the top here, you will have to apply another Hadamard gate, and this Hadamard gate, for example, if it is 0 plus 1, it will take you to 0. If it is 0 minus 1, it will give you to 1. Okay, so only point here is, so this represents a constant function, whereas this represents a balanced function. So if you get 0, you will be sure it is a constant function. If it is 1, you will sure it is a balanced function. Okay. So the functional values are same. The only point is that overall they can differ by a sign. So this is the logic. This is the step for the Deutsch algorithm. Okay, and it can be simply extended for the n-bit case. Of course, for the 2-bit case, it does not offer any advantage with respect to the classical algorithm, because after all, here also you are using 2 inputs, 2 gates, and in the classical algorithm, you can also use 2 queries for the function. However, as soon as you go to an n-bit string, then apply the Deutsch algorithm, there is a tremendous improvement in performance, and the steps are all similar like the one I did last time. Only thing, instead of a 2-bit string, x going from 0 to 1, 0 and 1, you have x going from 0 to 2 to the power of n minus 1. The superposition of 2 to the power of n elements is taken together. And actually all such Hadamard's, all such oracle functions and output Hadamard's are involved. And again, giving the final state, all the final outputs at 0 confirms to you that the state is a constant function. On the other hand, if you get 1, then the state is a balanced function. Okay. So in a summary, this is the Deutsch problem. So given a function which takes 0, 1 to map 0, 1 to 0, 1, 1 to 2 bits, then you have to determine whether the function is constant, which means that fx equal to 0 for all x, and or fx equal to half the time 0 and half the time 1. Okay, so in this case, fx is balanced. So classically, one needs exponential number of steps, whereas quantum mechanically, through the Deutsch algorithm, you need order of n gates. Okay, so for example, in the 2-bit problem, you needed 2 gates, whereas in the n-bit problem, of course, you need n gates. Okay, so you need so many Hadamard's because you will have so many arms. So instead of 2 zeros, 0, 0 here, you will have more number of zeros here, and you will need more number of Hadamard's. So this is the only difference. So you, instead of n 2 to the power of n, you will need on gates and only 1 query. So that is, 1 parallel processing will do the job for you. So this is the power of parallel computing, power of the Deutsch algorithm. So this is just again in a nutshell. So this is the circuit for you. So you are seeing. So if you have an n-bit string, you need n such Hadamard gates, and finally you have to measure on these gates. Okay. So big advantage is that you need order of n steps instead of 2 to the power of n steps. So this is the big advantage in this quantum computing. And quantum computing is not just limited to Deutsch algorithm. This is one of the most original examples. There are other examples also. Around the same time, Love Grover tackled this famous search problem. And you have to search for a needle in a haystack, or you have a large collection of numbers and you have to pick out one number. How do you do it? So this is an unordered n element search, and classically again you can imagine. So this is very simple to understand. If I give you numbers 1 to 100 and you have to say 100 balls, and I ask you to pick up one particular ball, then you have to start from one end and you have to sample through, you have to go through the whole sample. Okay. So in effectively of approximately you have to go through on average half the number of samples in hitting the right target, right ball you are searching. So in this case also order of n steps are required. However, if you handle this problem using a quantum mechanical algorithm, you will actually require not n steps but root of n steps, and for large n, this actually presents or provides a tremendous advantage. Okay, so Grover's algorithm can also be described, quantum mechanically. So this, for example, is the circuit of the Grover's algorithm, and again, the circuit, as you see, there are some similarities with the Deutsch algorithm. You start from bits, start from qubits, you apply Hadamard transformation, and then you have to devise a suitable quantum function or a quantum operation. Okay, so this can be done, and let me not go through the steps because I've already gone through. There is not much time left. I will also have to leave some time at the end for questions. So I will just have to forego this discussion of the Grover's algorithm. But in the last 10 to 15 minutes, let me talk of again an algorithm of quantum information processing which harnesses the power of entanglement in quantum mechanics, that is the non-local power. Okay, so this is just a slide on what quantum computers can do, but this is a general knowledge slide. You can go to your internet and check for quantum algorithm. You will find many algorithms. So there are many different candidates for quantum computers, and I'm happy that at least in this school, later on there are at least 2 lectures on quantum computers, so you can learn more on quantum computers from those 2 lectures. So now let me move to these are some computing, of course, problems with practical problems with computers. So these will also be to some extent discussed by both those speakers towards the end of this lecture series. So now let me finally move to this topic of quantum teleportation. Again, this is a large topic, but I will have to quickly run through some basic elements of teleportation, and I'm sure that this topic is also will be handled or has been handled by some of the earlier speakers or later speakers, but I will give you just my flavor, my little perspective on this topic of quantum teleportation. Okay, so for example, in quantum teleportation, you require an EPR pair and you require an initial state, which can be a photon in some quantum state, and then this EPR pair, out of this EPR pair, one particle goes towards this side, the other particle goes towards that side, and finally the idea is to recreate this state, photon, on the other side. Okay, and phi, and in this process, 2 bits of classical information is required. You can model this in a way of circuits that you are familiar with earlier, so there is nothing new here. Basically, again, the problem is starting from a 00 bit, qubit, you using that Hadamard, you create a superposition and create an entangled state that I just talked about earlier. So you create an EPR pair and send, in that EPR pair, you send one particle to the receiver side, one particle to the transmitter side. The transmitter side already has a qubit existing with him or her, say Alice, and in this qubit is indeed the message which has to be communicated to the other party on this side. And in order to communicate this message, again this party Alice uses one of these particles from the EPR pair, performs a 2-qubit gate, again performs the Hadamard operation, performs a measurement because there are 2 qubits, so performs 2 measurements, and instead of sending any quantum channel, just transforms or just communicates the classical outputs of these 2 channels, these 2 measurements, either 0 and 1, to this party who is here, and this party here, of course, decodes what the message from Alice is, and using the message performs a suitable unitary rotation, another quantum gate on this qubit which exists within this. Remember, this is nothing but one of the particles of the EPR pair, and finally the message is transmitted on the other side. Okay, so now it's a similar thing I will describe to you using the quantum mechanical state vector notation. So Alice has a qubit in state psi, alpha 0 plus beta 1, but she does not know anything about it. And now if she measures this state, she will destroy it. So Alice cannot measure this qubit and tell the answer to Bob. So this is not allowed in quantum teleportation. Similarly, Alice cannot give the state to Bob by classical means. So there is no classical means by which Alice can give this quantum state to Bob. And we also have to remember that there is this no cloning theorem. So this state cannot be exactly cloned and sent to Bob. So there exists no quantum channel for this purpose. But what they possess is another resource, which is an entangled pair of particles. So assume Alice and Bob share a pair of qubits that is prepared in an entangled state, and Alice and Bob have access to 1 qubit. Okay, 1 qubit of this 2-qubit state. So this 2-qubit state is written by phi, which is 0a, 0b plus 1a, 1b in the familiar Bell state that you know from many examples. So this is phi, and the state originally with Alice is psi, alpha 0 plus beta 1. So now on Alice's side, Alice has one qubit from this joint state and also her qubit, which is the original message. So her full state, total state, will be a direct product of her state psi along with this qubit, which I can write down like this. So this is nothing but a direct product of psi with phi. And pictorially, again, what one has to do, so as I'm saying again and again, this is an entangled source phi. One of the particles, the first qubit of this 2-qubit source, comes to Alice. Alice already has an initial state, and her task is to do some operation and transmit some classical information so that Bob, who has access to the second qubit of this entangled pair, can perform a suitable unitary rotation on his state and get back an exact replica of Alice's state. So this is the start, the task of teleportation. And then, so this is again repetition. This is Alice's state, meaning her first qubit and one of the 2-qubit states. And now what she does is just to perform a C0 gate on her 2 qubits. So if she performs the C0 gate on her 2 qubits, so the product state which was initially, which will go, this is not equal, of course, this will go to an entangled state of phi and psi, okay. And then taking that state, she applies the Hadamard gate to psi A, okay. So this is the result of this Hadamard transformation, the steps you can work out. And finally, again, one has to apply the C0 register. So this is an example of the C0 gate. I will not repeat it because most of you are familiar with it. This is a 2-qubit gate. So this is represented by a 2x2 matrix. So remember earlier, Hadamard gate and X gate, etc., are 1-qubit gate, which were represented by 2x2 unitary matrix, whereas this is a 4x4 unitary matrix. This is Hadamard gate for you, which we did earlier. Okay. So this is repetition of the same state. So this performs the C0 on her half of the register and then applies a Hadamard gate. Okay. So then what Alice does is to perform a measurement of her 2 qubits and tell Bob of her measurement outcome. Now, as soon as she measures the 2 qubits, she destroys her original state. And of course, the outcome of this observation, the measurement of Alice, is unpredictable. So what can Alice measure? So finally, the state, after all her operations, Hadamard, C0, everything, the state which is accessible by Alice is this. And in this case, you see that not all the state is accessible by Alice, but the first 2 qubits are accessible by Alice because the third qubit is already at the side of Bob. So Alice can only make a measurement on the first 2 qubits, and if she makes 2 measurements, what particular values can she observe? For example, she can observe either 0 and 0, she can observe either 0 and 1, she can observe either 1 or 0, and she can observe either 1 and 1 for her 2 qubits. Now, whatever she observes, she communicates to Bob her result of her measurement. For example, if she observes 0 and 0, then this state, which is this joint state of Alice and Bob, is already reduced to this. It is no longer in the superposition because observation of 0 and 0 reduces this state from a superposition of these 2 4 terms to only this term. So in this case, when Alice observes 0, 0, Bob is left with what? Alpha 0 plus 0, 1 plus beta 1. So in this case, this is nothing but the original message, original state that was there with Alice. So if Alice tells Bob that I have obtained 0 and 0, so what will Bob do? Bob will do nothing. That is, mathematically, Bob will just apply an identity transformation. On the other hand, if Alice measures 0 and 1, she will tell Bob that she has measured 0 and 1. And of course, by prior protocol, the state is known. Bob knows what to do. So Bob will just apply a sigma rect x rotation on this qubit and applying a sigma x rotation on alpha 1 plus beta 0. You can do it, simple exercise will give you back just this thing, alpha 0 plus beta. So again, the initial state is recovered. And similarly, if Alice observes 1, 0, Bob will apply sigma z. If Alice observes 1, 1, Bob will apply sigma y. So Bob can retrieve the final state. So this is the result of teleportation. So this relies both on superposition and entanglement. Okay. And of course, you have to keep in mind that this accounts for the probabilistic nature of quantum mechanics. Okay. Bob has particular actions to take. Before the start of the experiment, Alice cannot say that whatever I get, you take the same action. Depending on the outcome of her particular run of experiment, she has to communicate to Bob the observed values, and depending on that, Bob will apply unitary rotations. So this is about quantum teleportations, and so this is again a repetition. The task is to transfer the unknown state of a quantum system to a distant location. The resource entangled state shared by two distant parties A and B, and the protocol is as follows. Party A makes a measurement on the system to be teleported, party B transmits through classical channels some information to B, and party B makes a transformation on the system located within. And what is the result? The true copy of the original system, which was initially at A, is now transferred to B. The original system is destroyed at A, and you have to keep this in mind that the system S is never physically transported from A to B. So what are some particular physical implications of teleportation? So the state is unknown. It is an unknown state of a given system. The sender has no knowledge of the properties of S. So sender does not have any knowledge whatsoever of S. And at the end, S, actually the state disappears at A and reappears at B. And as this is a repetition, what is transmitted from A to B is not a physical state, but only some information. And this information can travel at most with the speed of light. So there is no faster than light signaling. There is no violation of any laws of physics. However, such a procedure cannot happen simply without quantum entanglement. There must exist a prior entangled state shared between Alice and Bob. Okay. So this question is that, so this teleportation is indeed a fascinating application in quantum information, application of quantum entanglement, but how can it be done practically? There are some, practically it has been of course performed, but there are some issues here. For example, in practical teleportation, any practical information sharing protocol, the state shared between Alice and Bob may not be a maximally entangled state. Why? This can happen due to preparation environment uncertainty, and this can certainly happen due to environmental losses. For example, during the stage of transmission of one of these particles or both these particles from the preparer to both Alice and Bob, there can happen losses. Okay. So typically what happens is that Alice and Bob do not share a maximally entangled state, but they end up sharing a non-maximally entangled state. So if they have such a state which they do not know, which some experimenter has prepared, but by the time it has reached them, they do not know what the state is. So will teleportation protocol work? Will they able to actually accomplish this protocol? And again, for those of you who are practically motivated, I should also remind you, or I should tell you, that this teleportation will be extremely useful once quantum computers are available. So this will enable people, help people distributed quantum computation. For example, you can have access to your small device sitting in Sikkim. I can sit in Kolkata and have access to my small device, but we can combine and do some marvelous, fantastic quantum computation, quantum algorithm, just by using quantum teleportation. So this will be of tremendous practical application once you have some more technology, some more practical aspects settled out. But as far as the purpose of this talk, we are asking a fundamental question that if this state is unknown and it is not maximally entangled, can Alice and Bob still perform teleportation? So I would have left it at that, and maybe last 15 minutes taken some questions, but since there are, okay, so there is one question. Let me try to see what this question is from Jatin Ghai. Do we need a classical exchange of info between A and B also for the data at B to make sense, as measurement of A is probabilistic? So of course, the classical exchange of info is certainly there. So that is the whole point of teleportation. As I've been saying again and again, Bob has to measure these two qubits and obtain an info that is either 0 and 1. And the output what Bob obtains, which is legible to observers like us, human observers, is nothing but classical info. This is either 0 and 1. So Alice has to inform Bob of this classical info. So therefore, this means that classical info is exchange, or more properly, it is sent from Alice to Bob. So the protocol has to work by both a quantum channel, which is an entangled state, and exchange of classical info. Okay, I hope this answers the question. And since there is no more question, let me just try to finish this lecture by just taking on this question and completing with one more topic, which tries to answer this question: how will such a teleportation protocol work, and or will it work at all? Okay, so this has to do with the area of entanglement witnesses. It is again a very important area in quantum information theory, which relies on some very useful notions in quantum mechanics, for example, Hermitian operators. So what is the motivation for this area? So all of us know that quantum entanglement, by now all of you should know that quantum entanglement is a useful resource for performing many tasks which are not achievable using laws of classical physics. And I can name many: teleportation, dense coding, cryptography, error correction, computation, so on and so on. Okay. So the question I asked in the last slide is related to this question, that given an unknown state, can I detect entanglement in the lab? Okay. How to detect entanglement by an experimenter? So for example, if you have an unknown state, can I say that this state will be useful for class information processing? If it is useful, I will retain it and do processing, because quantum information processing is also costly in terms of resources. I will have to apply gates and many transformations, so on and so forth. But if it is not useful, I will throw it away. So it will always be beneficial for me to know which state is useful. Okay. So how do I go about this problem? Again, I take a cue from quantum mechanics, which tells me that all observable operators are represented by Hermitian operators. So in this case, I construct certain Hermitian operators which can act as witness for this resource. So for example, I can construct Hermitian witness operators for entanglement, and if I measure the entanglement value of this operator in the given unknown state, then it will tell me whether this is entangled or not. So I can, in the lab, I can almost always easily perform this observation, because I can just take the unknown state and apply the observable on the state. Okay. So this is a method, and more generally, so this can be applied for resources of information processing, and in order to answer the question that whether quantum correlations are useful for constructing teleportation channels. So the particular question here is that, for example, if I have a state, given an unknown state, can we tell that it will give rise to quantum fidelity? By the way, I did not define quantum fidelity, but maybe in the last lecture I just mentioned, because these states which I mentioned here, for example, if my target state is maximally entangled and what I get is not this target state, then, but on the other hand, I get this state with alpha and beta as coefficients, then I can calculate the overlap of this state with this state. Just I can apply phi, get to psi, and then I can get some number. That number will give me fidelity. If alpha and beta are both 1 by root 2, I will get 100% fidelity. If alpha and beta are not 1 by root 2, but far different from 1 by root 2, then I will get less and less fidelity. Okay, so they're very simply fidelity, you can understand that like this. So the question is, how does one detect whether a given state is useful for teleportation? And a similar question can also be applied for other resources. For example, you have had a flavor of what are pure and mixed states. So for example, if there is decoherence, a pure state goes into a mixed state. But if an experimenter has access to some unknown state which has interacted with the environment, can one say how much pure it remains or how much mixed has it become? And in order to answer such questions, one of the very basic methods is to construct witness operators. Okay. So the motivation for witness operators, motivate for teleportation is already repeated. Teleportation is a prototypical information processing task, and the present challenge is to push experimental frontiers. By that I mean that teleportation has already been shown experimentally. How far can we teleport, or however larger objects can we teleport? That remains the question. These remain old references. By the way, many of you are aware that the Chinese people have claimed, by Pan's laboratory, they've claimed that teleportation has been successful from artificial satellites to the Earth. So you see how this subject is becoming more and more fascinating for communication. Okay, and also it can be used for distributed quantum computation. So this is the practical motivation, and from the theory side, we know that not all entangled states are useful for teleportation. Okay, so if you see, for example, there is this work in 2010 where we showed that a particular type of state, even in 2x2 dimensions, which is entangled, which has a definite finite value of concurrence, measure of entanglement, but it is not useful for teleportation. So, but for those types of states, can we say from some other means, from using a witness, that whether these are useful for teleportation? And certainly we can do so. We can apply an object, we can apply a mathematical object, and we can conclude that these states are useful for teleportation. So I will not go into the details. Anyway, I am running out of time, so just to give you an idea. So we were thinking of these problems almost 10 years ago, and then indeed we worked out, I and my ex-students, we worked out this problem of entanglement witness operator for quantum teleportation, and the purpose of this was published in PRL many years ago, 2011, probably that time some of you were in school, so it is old for you, but the point is just to show you this slide is that this is not the end of the story. This represents the first example on one hand of a witness operator for quantum teleportation, but subsequently other examples of witness operators for other information processing tasks have also been performed, also been done, some of them by our group, some of them by other groups at various places in the world. And not only a simple teleportation witness, other areas, I mean, other progress has also been made. For example, given a witness operator, how many states will it be able to certify, whether it is optimal, how can we go to more and more optimal witness operators. So this remains the subject of witness operators, which is a broad subject. So some of you are interested can try to read it. And basically through which I come to the end, to the summary of my talks. So in these two talks, I tried to motivate for you some of the foundational questions in quantum mechanics, and by the study of them, how we can actually go towards investigating quantum information. So, for example, I studied from I began from the superposition principle of quantum mechanics. This leads to from bits to qubits. Then we discuss quantum example, quantum entanglement, which is a special property of physical systems that is easily manifest at the micro level. The challenge is to make this manifest not simply at the micro level, but maybe at the macro level, at least from the point of view of large physical distances, spatial separations, and also from the point of view of large physical devices in quantum computation. So as I said, so these properties of superposition and entanglement leads to the possibility of performing entirely new and interesting tasks. And this has brought about the prospect of a second quantum revolution through upcoming technology. So this is indeed going to come in our lifetime, maybe if not in my lifetime, at least in the lifetime of you young students. You will see practical quantum computers, and already we are seeing practical quantum communication in terms of practical key generating devices. These are available in the market. But more importantly, we see basically I am a theoretical physicist. for me, the most charm of this subject is trying to understand these deep-rooted puzzles, these enigmas, these paradoxes, and indeed the efforts of understanding these problems right since the beginning of quantum mechanics for more than a century have given rise to so many fascinating new phenomena, new understandings of quantum mechanics, quantum information, quantum non-locality. Okay, so the road ahead is very fertile. So there are many, many, many questions that as young researchers you can ask, and some of these questions will also be dealt with at some length during the course of the following lectures in this conference. So I've just listed, I think, 4 or 5. They can be many. They can be more than 20, 25, 50 such basic fundamental questions or basic questions of practical importance you want to ask, you would like to ask as a researcher in this subject. And I end my talk with this, just a slide of pictures to give you a certain flavor of different directions in communications, computations, and fundamental questions that one can ask. There are challenges at the present time. So thank you very much. I think I've spoken for a long time. I've taken advantage because at the end there were not many questions, but in the remaining 5 minutes or so, if there is any more questions, I will be happy to answer these questions for you. Okay. Yes. Oh, thank you. Thank you so much. And Sikkim is such a wonderful place. And I would certainly lose no opportunity to accept your offer. But I would also like to interact with the new department that is coming up there. And you people are so keen. You are organizing such a wonderful course of lectures. So many young students will be benefited by that. So thank you for this initiative. Thank you so much. Thank you.